So with that out of the way, let's take a look at our next topic, which is the motor effect. Sorry, hydrate, dihydrate. Um, we've looked so far at our electric fields, we've looked at our magnetic fields, and now we're going to take a look at, well, how can you actually maybe start to use them in some real applications. Now, the motor effect is defined as a current carrying conductor the fact that a current carrying conductor in a magnetic field experiences a force. I'll give you a much more concrete definition in just a second, but basically what this tells us is that if you have some current carrying conductor, i.e. like a wire or a piece of metal, basically if you have some kind of current flowing and you chuck that inside of a magnetic field, it's going to experience a force. Now, I've got a couple of hot tips that I want to include throughout my lecture, and my first one is just the fact that whenever you're writing an extended response or even just like a written response in general, I really, really highly encourage you to use jargon in your writing. So jargon basically just is referring to those kind of technical words, those little spicy words you can include in a response that just really show the reader that you understand what you're talking about, that you really, really understand the things that you're discussing. And there's a couple of big benefits to using them. Number one is that they show that you've studied, they show that you understand them, particularly if you're using, and side note, you should always really only use your jargon and your keywords in the right situation. I like don't be talking about the motor effect when you're dealing with like projectile motion or something like that. Um, but if you drop them in at exactly the right time, they will just wow your like reader, wow your marker. They'll be like, wow, this person, this student just knows absolutely everything. They're so smart. Let's give them a band six right on the spot, which we love. We stand that. The other reason is that it will really help to condense your writing a lot, because I know something that a lot of physics students struggle with is like you read a question and you're like, I know how to answer this, like I know exactly how I'm supposed to do this, but then like there's like three lines of writing like that the question has given you, and you just write for an entire page. The reason a lot of times you're doing that is because you're trying to explain things that like other people have come up with words for, and those words are our pieces of jargon. So for example, if you're trying to refer to the force that a current carrying conductor experiences, instead of saying, this wire will experience a force, you can just refer to the motor effect, which is what we're talking about here. Um, so why does this happen? Now, I want to preface this by this is a slightly dodgy definition, so it's not 100% accurate in every single way, but it gives you a good idea as to like why it happens in the first place. Basically, if we've got our station, we've already seen how a stationary electron experiences an electric field, and a moving electron experiences or has both an electric field but also produces a magnetic field as well. Therefore, all charges are going to be surrounded by a magnetic field. Therefore, a current, which you may remember is just a whole bunch of charged particles moving together, is also going to be surrounded by a magnetic field. Now, you learned this in year 11. You may remember that, like, if you have some current carrying conductor, you can figure out the direction of the magnetic field around it using the right-hand grip rule. So just to be very clear, this is different to the right-hand palm rule, which we experienced before. This is the right-hand grip rule, where basically you can point your thumb in the direction of the current, and your fingers will then point in the direction of the magnetic field that's surrounding the current. So in this case, let me draw a slightly clearer one. If we've got a current that is pointing downwards, you can stick your fingers around, like you can imagine that you're kind of gripping or grabbing onto the coil or the piece of wire, and that will indicate the direction of the magnetic field that's going around it for you, which is really, really sweet. And in fact, so let me try and draw that. It's like moving, that's bad, a bad drawing. It's moving around like that. Um, I'm really not great at drawing, hey. Anyway, yeah. We can also represent that instead, now that you've seen our lovely notation for going in on one side and out on, like, for going in and out. You may notice that, like, if you imagine you took like a clean swipe of my hand, on one side of my hand the field is going into the page, whereas on the other side of my hand the field is coming out of the page. And we can actually draw that down here. We can draw a whole bunch of X's down along here to represent how it's going into the page on one side, and a whole bunch of dots to represent how it's coming out of the page on the other side. Okay, That was a lot. Let me just quickly recap. So we know that a charge, when it starts moving, produces a magnetic field. A current is just made up of a whole bunch of charges, and so as a result, it produces a magnetic field around it, and we can figure out what the direction of that magnetic field is using the right-hand grip rule. Um, just in general, I'll try and explain this a little bit more later on, but because we've now seen these two different right-hand rules, I would encourage you to try and use this rule more. Like the palm rule that we saw beforehand is pretty much exclusively just used for the case where you have either the motor effect by itself, which is the case we're about to see coming up, or you have a charged particle experiencing a force. Pretty much everything else, when it actually, okay, whenever we're dealing with a force, we use the right hand palm rule. Whenever we're dealing with like the relationship between the direction of a current and a magnetic field, we use the right hand grip rule is probably the way I'll try and explain it the best. And I'll try and like rag this up a lot more as we go through the rest of the lecture. But I just know that that's something that a lot of students struggle with is like now that we've got these two different right hand grip rules, where do we use one? Where do we use the other? Palm rule is for force. I don't know, maybe like it looks like you're trying to high five someone. And when you high five someone, it applies a force on them. That was horrific. I'm so sorry, but that was me trying on the fly. Okay. Um, Whereas our grip rule, right, is like when you're trying to find the relationship between current and magnetic field, and when you grip someone's hand, you're building a relationship in some way, shape, or form. Uh, that was a stretch. I'm sorry. Please forgive me. Let's move on. So the magnetic field produced by currents can interact with another external magnetic field, and just like when we had our magnetic fields interacting beforehand, we experience a force once again. Now, this is basically the same magnetic field force. It's just that instead of being the magnetic field being applied to a single particle, it's the magnetic field being applied to a whole bunch of particles at the same time in the form of a current. Now, if you're particularly cheeky, you will have noticed that this topic is called the motor effect. We won't actually talk about motors until the very last topic, but the reason it's called the motor effect is because basically what you've got here is you've got a force being applied to a wire, i.e. a force rather than just being applied to a single particle, a force is being applied to a whole thing at the same time. Um, so the way you figure out the direction of this force is through the right hand palm rule. It basically works exactly the same way as our right hand. It works the same way as our right hand rule for our forces on single particles. The only difference is instead of having the direction of particle, it's the direction of the current, which is basically the same thing, right? Because a current is just a whole bunch of particles moving in one direction. So just to quickly recap, you can figure out the direction of the motor effect force by pointing your fingers in the direction of the magnetic field lines and your thumb in the direction of the current, and then the force is moving out of your palm. Yeah, that's pretty much all there is to this. Just a quick reminder, your current is always pointing in the opposite direction as the flow of electrons. So because we imagine current as being the movement of positive particles, that's always moving in the opposite direction as the flow of negative particles, which is a whole lot of fun. Now, the magnitude of the force, well, it's dependent on the size of the magnetic field, it's dependent on the size of the conductor, and it's the size, i.e. like the size of the wire, and it's also dependent on the amount of the conductor that's actually exposed to the magnetic field, and the angle as well. Which means that our formula actually takes a very similar form to our charged particle formula, which is our F equals QVB sine theta. Like there's a lot of similarities between the two. Now there are reasons for that because basically the number of charged particles in a particular region you can kind of convert between the two, and it's a lot of fun. And it really is essentially the same formula. It's just for two different situations. We use this formula if we're trying to use a single particle. That's where we use this one, whereas this one we use when we have some kind of conductor, some kind of wire. Is where we use that. I can't spell conductor. One of the fun things about me is I find when I'm talking and I'm trying to write, my spelling just falls off a cliff, which is lots of fun. So just quickly, our force is measured in newtons, our length is measured in meters. This is the amount of stuff that's in the magnetic field. Sorry, our current is measured in amps, and our magnetic field, once again, is measured in Teslas. I realized I never gave you a quick little like recap, but just in case you forgot, current is just the motion of little particles inside our wire, and it's measured in amps. It's cool, which is lots of fun. So let's actually jump into a practice of trying to use this formula. Remember, as always, if you want to have and if you want to give it a crack yourself, you can go down into the Slido down below, and please do give it your best shot. It should be fun. So in this question, we're going to calculate the magnitude of the force on a 2-meter long power cable, which is carrying 10 amps of current if it is laying at an angle of 30 degrees to a 2 millitesla magnetic field generated by an MRI machine. So remember, we're going to be using our formula. Force is equal to length times current times magnetic field times sine of theta. For this case, I reckon it's probably a good idea to draw out a cheeky little diagram. So we can say here is our magnetic field. It's our 2 millitesla magnetic field. Wow, so crazy. Wow, Tim, you're such a good drawer. That's crazy. Thank you guys. So wonderful. See, I'm going crazy by not having you guys to speak too loud. Okay, I'm sorry. Okay, so here is our wire. Let me actually try and grab a different color this time, so I'm not just drawing full red on red. Here is our beautiful wire. It's laying, this is a pretty dodgy 30 degrees, but here is our angle of 30 degrees. And I know I realized I didn't mention it when I brought up the formula, but basically the sine theta works in the exact same way as it did for the single individual particles like before, right? It reaches a maximum when our y is acting perpendicularly, and it reaches a minimum when it's acting in parallel. Now, just the reason I think that this diagram is useful is because it shows to us, oh, in this case, as much as Tim may like to pretend that the angle doesn't exist, in this case, it is actually going to be important. So let's quickly write down all of the numbers we know. We know that our force is measured in newtons, and that's actually what we're looking for. Sorry, we're trying to calculate the magnitude of the force. We know that the length of the power cable is 2 meters long, so we could write that down as 2 meters. We know that it's carrying 10 amps of current. It's a very powerful power cable. To be fair, it's not that crazy. Sorry, it is semi-realistic. It is crazy current, but like it's not wild. Our magnetic field is given to us as 2 millitesla. Remember the multiplier milli is times 10 to the negative 3. And finally, we're told that our angle is 30 degrees, so we could write this down as theta equals 30 degrees. And so now we've got all these numbers, we know what our formula is, we can kind of play match, join the dots, and just sub all of our numbers in. We can check off, yes, I know what every single thing means, let's just chuck them in the formula. So we can say our force is equal to our length, which is 2 meters, times our current, which is 10 meters, times our magnetic field strength, which is 2 times 10 to the negative 3, times sine of the angle, which is 30 degrees. You can chuck all of that into your calculator. You get 2 times 10 times 2 times 10 to the negative 3 times sine of 30, which if you do all of that, you end up with 0.02. Remember, it's a force, so it's measured in newtons. We could also write this as 20 millinewtons as well. And that is going to be our force. And you know what? Just to practice some things, let's say hypothetically the direction of our current is down there. Our current is flowing in that direction. If you want to, I know this isn't going to be on the Slido down below, but if you want to just quickly practice which direction is that force going to be acting in, well, if you do that, you should be able to figure out, okay, our current is moving downwards, so sort of line your thumb up a little bit. This one's going to be slightly tricky with the direction of the current. You can put your fingers in the direction of the magnetic field, and all of a sudden I'm realizing I've kind of made myself, my thumb doesn't go that far, right? My thumb kind of sucks. But if I can kind of imagine what would happen if I could like dislocate my thumb or whatever to get it round. Kind of. It's a bit of a struggle, right? But anyway, my fingers are pointing like that, my thumb's kind of pointing around like that, and as a result, my palm is pointing towards myself, so I can say that the force is going to be coming out of the page, right? The force is pointing back towards me, which is a lot of fun. if you could actually do that, chuck it in like a Q&A or something, because like, man, I would be very impressed if you can move your thumb that far. My thumb is hurting. I regret doing that, okay? Um, but yes, that is our lovely drawing that I did before. That is our stuff. Cool. Now let's have a cheeky bit of practice with a past HSC question. This is one that I got from the 2012 HSC. Just to show you, this is actually the kinds of things that you might be dealing with in your HSC proper. So in this situation, and once again, this is an HSC question. We've just done a practice. There's not a ton of difference between what we've done in this question and what we've done in the last one. So I really do encourage you, if you want to give this one a bit of a practice by yourself, pause the video and go down to the slider and give it a crack by yourself. Hey, doing an HSC question in January, that is what I love to see, all right? You're really getting on top of it. But yeah, let's jump into this one. So a current carrying conductor, or current carrying wire, sorry, passes through a region of uniform magnetic field with a magnitude of 0.05 teslas, and as a result, it experiences a force with a magnitude of 0.03 newtons. Our question is, what is the current going to be? Well, it is slightly trickier than the one that we've just done, but once again, we can kind of use our same technique. We don't have to draw a diagram because they've already given us a diagram, which is very much, thank you, Nessa, stand this question. But let's quickly write down all of the information that we've been given. So we can say that our force is equal to 0.03 newtons. So we can chuck down force is 0.03. And because this force that it's experiencing, remember, is the motor effect, we can use our motor effect formula, or force on current carrying conductor, to just quickly jot down, okay, we know that this force of 0.03 is equal to the length of the conductor times the current passing through the conductor times, sorry, B, I forgot B, shouldn't forget B, that's unfortunate. Must remember that B is something that exists. We need justice for B. Times our magnetic field times sine of theta. Now, because we're looking for our current, this is the thing we're looking for, we can quickly rearrange the formula, right? We can divide across by L, we can divide by B, we can divide by sine theta to get that our current is equal to the force divided by the length times the magnetic field times sine of theta. You can do this in any order that you like as well. I just prefer to rearrange my formula and then sub in numbers rather than sub in numbers and then rearrange my formula. But now that we have rearranged the formula, we can start subbing in some of our, well, we can write down the rest of our numbers and then we can start subbing some of them in, right? So our checklist is we need the force, we need the length, we need the magnetic field, and we need theta. So we've got force, bing, bing, bing. What other numbers do we have? We've got our magnetic field strength, so 0.05 teslas. So that gives us B, sorry, I'll write down B is equal to that. Which leaves us with our length and our value of theta. Let's start off with our length. Now, we aren't given any other numbers in our question, which means a good idea is probably going to be turning to our diagram and seeing, okay, how can we figure out what our length is based off the diagram? And if you look on our diagram, we're actually given a couple more numbers. We're given an angle of 30 degrees and we're given a length over here of 0.2 meters. Now, our length, remember, is the length of the wire that lies inside the magnetic field, which is basically going to be this side length over here, this whole diagonal that passes through the magnetic field, which, looking at it, we can actually kind of interpret as just being the hypotenuse of this triangle. We can kind of draw a little triangle where this side is 0.2, this little angle is 30 degrees, and we are looking for the length of this third angle over here. So we can do this using a little bit of cheeky trigonometry. Even though they haven't drawn that out as a right angle, we can probably assume just looking at it, it's basically a right angle. And so we can figure out this third side length using our lovely trigonometry. So because we are interested in the hypotenuse and we know what the opposite angle is, probably what we should use is our sine. So we can say sine of 30 is equal to our opposite side divided by our hypotenuse. Our opposite side is what we know, which is 0.2 divided by our hypotenuse, which I've I've written it as the question mark. Maybe that's not the most clear pronumeral to use, but Now that we've got this formula, we can rearrange. Let me write it slightly clearer up here. So we can say sine of 30 is equal to 0.2 divided by our question mark. Rearranging it, we then get that our question mark is equal to 0.2 divided by sine of 30, which if you chuck that into your calculator, you end up with a value of 0.4, which is quite nice. It's quite a nice, neat answer. But yeah, that is our length. We now know that our length is equal to 0.4. So checking that off our list, we've got our force, we've got our B, we've got our length, which means all that's left is our value of theta. If you want, quickly pause the video and try and figure out what that value of theta is going to be, because it's a little bit of a tricky one. But if you've had a little bit of a pause, had a little bit of a think, had a bit of a look at the diagram, right? I have low-key, sorry, I have kind of drawn over the diagram here. So let me get rid of that so you can see it slightly clearer. But at the top here, we're told that the direction of the current is down here. Current's pointing downwards. But the direction of the magnetic field is actually into the page, right? So if you try and like make that on your hand, right? Your thumb is pointing in that kind of like downwards diagonal direction, but the rest of your fingers, because we've got all those X's, right? The arrows moving away from us, the rest of your fingers should point into the page. And what you notice is that even though it's kind of tricky to draw here, the magnetic field is moving away into the page, that's still perpendicular. They're still at a right angle to each other. So even though we're given this cheeky little 30 degrees over here, it's a bit of a red herring. It's a bit of a trick to try and trip you up. Instead, our theta is actually equal to 90 degrees. That's actually what we're dealing with over here. Still the classic 90 degrees. And so as a result, remember, sine of 90 is just equal to 1. And so we can just get rid of that. We can ignore it. We don't have to worry about it anymore. So our force is equal to 0.03 divided by our length, which is 0.4, times our magnetic field, which is 0.05. Chuck all of that onto your calculator, 0.03, sorry, I just typed 0.3 divided by 0.4 times 0.05, which if you put all of that in, you end up with a current of 1.5 amps. And so that is the direction of, sorry, that is the value of our current. If you want to be super specific, you can say it's moving on that diagonal. But I mean, we were given that in the question. So to be honest, I don't think it's like one of the most important details you need to include. All right. Hopefully that made a little bit of sense. Let's move on to the next hot tip, which is that we have a question, just like that one where there was quite a bit of work going on, right? Like we needed to rearrange the equation, then we had to like do a little bit of trigonometry to find out what one of our values was, and then we had to figure out like, hey, what's actually happening here? So I really encourage you in like more complex questions like the one that we've just done there. It's often really valuable to bring along a highlighter and highlight as you're reading through the question. You can highlight all of the different parts of the question, all of the different numbers that you're given, maybe like the directive term, what you're trying to find. You can highlight all of the important things, and that means that like you don't like forget that they're there, because I find that one of the biggest struggles of physics students is you just forget like what you've used and what you haven't used, like what numbers you've actually got available to you. Like in the last question, we may have struggled because we may have just forgotten that these things were available to us. We may have just forgotten that the diagram existed. And if we did that, trying to find the length would be basically impossible because we don't have the things that we needed to figure out what the length was. Whereas because we did know what they were, like it was all fine. We did know what it was. Okay, so just like we can have some external magnetic field applying a force onto a wire, if we have two wires that are both producing magnetic fields, we can have some like degree of interaction between the two magnetic fields. And this is what we call the force or the interaction between two parallel, or not necessarily parallel, but current carrying conductors. So essentially what you've got going on in this situation is rather than like one wire and an external magnetic field or something, you've got a wire and then another wire next to it. And because these two wires are both producing magnetic fields, their magnetic fields will sort of interact with each other and cause some sort of force between them. themselves. Now, the magnitude of the force per unit length between the two parallel wires is given by this formula here, where it's the force divided by the length is equal to this funny little guy, which is called the mu, divided by 2 pi times our current 1 times our current 2 times divided by our radius. Just as a quick side note, as always, this formula is on your formula sheet. Don't worry, I will be very direct and very obvious if you ever encounter a formula that is not on your formula sheet. But just to quickly break it down a little bit, our force is the force that we're very nice and familiar with, which is our force measured in newtons. Our length is the length of the two wires, right? So this is if we've got two really, really long wires, it's however long they are. If it's the length of two really short wires, it's however long they are. You might be wondering why we write the wires and why we write it as force divided by length rather than just force. And the reason for that is because the length of these wires could technically be really long. Like imagine we're dealing with power wires or something like that, like the power grid system, those wires, overhead wires that you might see that go along your street, but then also those massive wires that literally go cross country. Those wires run parallel to each other for a very, very, very long time. And so as a result, your length would be massive. So if you did force is equal to mu zero blah 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 times length, you would end up with an absolutely huge force, right? But that's not particularly relevant because your wires are so long, and so as a result, the force between 2 points on the wire may not actually be massive, even though the force itself is absolutely huge. So instead, what we do, rather than looking at the force in its entirety, is we just look at the force over a little tiny section of wire, which we call the force per unit length. So anyway, yeah, the force is force. L is the length of our wire that we're trying to analyze. Mu naught is what we call the magnetic permeability constant. It's equal to a 4 pi times 10 to the negative 7. Don't worry really what it actually means. It's kind of like how easily magnetic field lines are able to propagate. Now you're given it on your formula sheet as yeah, you're given it. Are you given it on your formula? You are given it on your normal formula sheet, just not this cooked version that I've managed to find. I'm so sorry about that, guys. Um, yeah, it's equal to 4 pi times 10 to the negative 7. However, I suppose what this formula sheet has is it's instead got this whole thing, which is mu naught on 2 pi, which we've got written as 2 times 10 to the negative 7, which is what you get if you divide 4 pi times 10 to the negative 7 by 2 pi. You end up with just 2 times 10 to the negative 7 instead. So it ultimately means the same thing. So this whole thing, when you combine it together, just gives you 2 times 10 to the negative 7. Then your I1 and your I2 are just the currents that are passing through your conductor. So it doesn't matter which order you do it in. One of them can just be called I1, one of them can just be called I2, and R is the distance between your wires. Sometimes on some formulas it might be written as D. But yeah, it's just how far your two wires are apart from each other, because once again, if you bring them further and further away from each other, they aren't going to be experiencing as much of a force compared to each other, which is how it works. Now, one of the weird things that happens with wires is our parallel wires is if normally what we experience is that if two things are opposite to each other, they're going to attract, whereas if two things are the same, they're going to repel each other. But this is the one case where this is not true, right? So if we have two wires that are pointing in the same direction, i.e. if we have two currents moving in the same direction, they're actually going to attract each other. Whereas if we have two wires that are moving in opposite directions, they are actually going to repel each other. Now, that might seem really counterintuitive to you, but the reason it happens is actually because of the opposites attracting, but not because of the wires, it's because of the magnetic fields that our two things are forming. So if you imagine, let me see, let's flip back. I don't have a nice slide. Let's just do it here. So imagine you've got two wires that both are moving in the same direction. You can use your right-hand grip rule to figure out what direction the magnetic field generated by these two wires is going to be. So if we do it on the left-hand side, we can see that on the left hand of the left-hand side, it's kind of coming out of the page is the magnetic field, whereas on the other side, it's kind of going back into the page. We've got all of these crosses over here. And if you do the same thing on this wire over here, you can see the exact same thing is happening, right? Like on the right-hand side of our curl, sorry, and just, I don't think I said it, but just remember, because it's a wire, we use the grip rule to figure out we're looking at the relationship, right, between a current and a magnetic field. So we use the grip rule. So once again, it's coming out of the page on the left-hand side, and it's going back into the page on the right-hand side. And then you might notice, oh, look at this space in the middle. We've got, it's going in on one side and out on the other. That means those magnetic fields are going to be opposite to each other. And guess what? Those magnetic fields are going to attract each other, which is why when our currents are moving in the same direction, we actually get this force of attraction. Whereas when you've got these currents that are moving in opposite directions, right? Let me do this again. We've got one wire that's moving up. We've got one wire that's moving down. Use your right hand grip rule. On the one side, it's coming out of the page over here. On the other side, it's moving into the page over here. Down here, it's moving downwards, so it's coming, then because the current is moving downwards over here, you can point your thumb down. It's moving into the page over here, and it's coming out of the page over here. Look at how these magnetic fields are going to interact with each other. Ba-bow. They're both moving out of the page, coming back towards us, and so as a result, they're moving in the same direction, and they don't like that. And so as a result, they are going to repel each other. So if you didn't take away any of that, the key takeaway here is that if you've got these two currents flowing in the same direction, you get a force of attraction, whereas if you've got two currents moving in opposite directions, you get a force of repulsion. So if your two currents are flowing in the same direction, the two wires will attract each other, whereas if they're moving in opposite directions, they will repel each other, which is a lot of fun. So with that all out of the way, let's have a go at a little bit of cheeky practice. And as always, if you want to have a go at this question by yourself, you can feel free to do it in the Slido down below. But if not, let's jump into it. So 3 parallel wires, X, Y, and Z, all of length 1 meter, all carry electric currents. A force of attraction is produced between X and Y. There is zero net force on Y. Our question is, what is the magnitude and direction of the current in the position X? Okay, let's dig into this a little bit. There's quite a bit of stuff going on. First of all, let's kind of write down all of the information that we have been told. We know that our length is equal to 1 meter, and that's true for all of them, right? We've got our length is equal to 1 meter, and that's, I suppose the reason that's so nice is it means that in our formula, F is equal to mu 0 on 2 pi times I1 times I2 all on R. We don't really have to worry about the divided by L section because our L is just equal to 1. So we're basically just doing divided by 1, so we can just get rid of that. So now that that's out of the way, we don't have to worry about our length anymore. It essentially just gives us a bit of a nicer formula. Now, we're told that we have a force of attraction between Y and Z. Basically, that means that there's some kind of force that is pulling Z back down. And sorry, there's no other numbers. There's no really isn't any other numbers in the question. There's some numbers on the diagram, and I promise we will get to them when we get to them. But because there's no other numbers in the question, we can kind of just move on to start digging into what other things we are told in the question, right? So we know that there's a force of attraction between Y and Z, which means that there must be something pulling Y down. Now, if you remember back to a couple of slides ago, I said that the force of attraction will occur whenever we have two currents moving in the exact same direction, which means that Z needs to be pulling, needs to have a current that is flowing in this direction, which is useful, but we're not really looking for the direction of current Z. We're looking for the direction of the current in X. However, intuitively, we can think about the fact that there's no net force acting on Y, which basically means that if there's some force that's pulling Y down towards Z, there must be an equal and opposite force pulling it back up towards X. Just to go over that again, we're told that there's zero net force on Y. Basically, Y is chilling by itself. There's nothing that's sort of affecting it. But we know that there's a force that's pulling it down towards Z, which means that there needs to be an equal and opposite force pulling it back up towards X, which would be, if you look at this, this is going to have to be an attractive force acting between y and x, which means that in order to get that attractive force, we need to have x and y moving in the exact same direction. So essentially, we need to have the current that is flowing through x, we need it to be pointing in the same direction as y, which means we can answer half of our question just off the bat as saying, we can say the direction of that current is moving over towards the right. So we could say direction is over to the right. Let's make a jot note of that, because now I guess we need to get into some of the slightly spicier stuff, which is we need to actually calculate the force between, we need to figure out what the current, the magnitude of the current in X is going to be. Now to do that, we can use the exact same process, which is that we said the force acting on y due to z is going to be equal and opposite to the force acting on y due to x. So we could kind of write that as saying the force due to x has to be equal to the force due to z. Now we know what the current in x and y are, so now let's actually start writing down some of our other pieces of information. So we know that the current in y is equal to 20 amps. We also know that the current in z is equal to 20 amps. We know that mu naught on 2 pi is equal to 2 times 10 to the negative 7. You can also just write that as mu naught is equal to 4 pi times 10 to the negative 7. It's up to you. And we also know that the distance between y and z, which is our radius, remember, is equal to 30 centimeters. Now, our radius is measured in meters, which means we need to convert this into meters, and so that's going to be 0.3. So that's our force due to z. So quickly writing out the formula, we can say that the formula of the force due to z is going to be mu naught on 2 pi, all times our I of y times our I of z, all divided by the distance between them. And look at that. If you go through, you can actually check off all of these numbers. We know what all of these numbers are. So you can start slapping some of these numbers in. We've got 2 times 10 to the negative 7 times our current, sorry, that's our mu naught on 2 pi. Our Iy is equal to 20 times our Iz, which is also equal to 20 divided by our radius, which is 0.3. Chuck all of this in, you get 2 times 10 to the negative 7 times 20 times 20, all divided by 0.3, which is equal to 2.67 times 10 to the negative 4 newtons. Okay, done quite a bit of calculating, but unfortunately this is only half of the trek. All right, we haven't quite made it all of the way to the other side. We still have a little bit of work that we need to do. So save that number on your calculator. If you just quick side note for calculator techniques, if you're not sure how to save that on your calculator, you can use the shift button. I'm not sure where my camera is. Yeah, you can use the shift button. Then you should find a button that says like STO. For me, it's like my RLC button, somewhere about that, hopefully. If you press that and then you press any one of the letters, like the alphabet letters on your calculator. So for example, I've got like A, B, C, D, etc. If you press any one of those, you should see a little number pop up the top that says like answer has been saved to A. If you do that, you can then come back to it later, and it's a whole lot of help. Other quick side note, because we're using a lot of scientific notation, if you find the button that says like ENG on your calculator, once you've got an answer like active on your calculator, you can press the ENG button and it'll slap it into scientific notation form. So you don't have to sit there and count up all the zeros. Which funnily enough, I didn't actually know that that button existed during my HSC. I found it during like the first week of uni, and I was devastated because I spent my entire HSC counting up zeros to do scientific notation, which sucked. But yeah, anyway, back to the question at hand. We now know what our force due to Z is. We want to calculate what the current in X is, and to do that, we kind of need to extrapolate out our force due to X. Now, I'm going to quickly get rid of some of this stuff. If you want to, you can flick back a couple of frames on the video and save it wherever it was, but hey, it's a recording. This is one of the advantages of a recording, I guess. You don't have to worry about making sure everything's available live. Okay, let me flick back to my pen and let's do the second half of the question. So we now want to figure out what the force due to X is, and we said that the force due to X is equal to the force due to Y, which we calculated as 2.67 times 10 to the negative 4. One more side note. I know that I wrote this as 2.67. It's 2.6666666666 repeating. Keep it in exact form. Don't round it like actually on your calculator. Keep it in the exact form. That's why I like to save it. Don't rewrite this in your calculator as 2.67. It means you may make mistakes. Don't round any of your numbers until you get to the very end. If you wanted to be using really actually good technique, you could write this as 2.6 and then just like dot 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 times 10 to the negative 7. I'm just lazy is essentially what's going on here. Now our formula for fx is mu naught on 2 pi times the current in x times the current in y, all divided by our radius as being equal to 2.67 times 10 to the negative 4. You can rearrange all of this to solve for our current in x. So rearranging that gives us our ix is equal to 2 times pi times our radius times 2.67 times 10 to the negative 4, all divided by mu naught, all times our iy. And so now we can just start subbing some numbers in. So we can have our 2 pi times our radius, which is that our radius in this case is 35 centimeters, 75 centimeters, which we can convert into meters as 0.75, times our 2.67 times 10 to the negative 4, all divided by mu naught. Remember, mu naught is equal to 4 pi times 10 to the negative 7. This time, I mean, yes, I know I could simplify it as like 2 times 10 to the negative 7, whatever. This time I'm not, I guess. And then our IY is 20 amps. So you can chuck that into your calculator, all of those numbers. Let me clean this up a little bit, but you can chuck all of that, chuck it in your calculator and see what you get. So 2 pi times 0.75 times 2.67, except I saved it before, so I'm going to use the exact answer, times all divided by 4 pi times 10 to the negative 7 times our 20, which if you do all of that, you end up with a current of 50 meters. 50 amps. I don't know why I said a current of 50 meters. Our current is 50 amps. And there we're done. We can kind of combine these two parts of the answer together. We can say it's 50 amps moving to the right. But that right there is our current in X. So just to sort of recap what we did, we first of all used what we know about attractive and repulsive forces in currents, between currents between two wires. And we used that to sort of figure out what direction this force needed to be. We used the fact that there's no net force on y, and the only possible force that we could have was the force due to x to figure out, like, okay, it needs to be an attractive force pulling us up back towards x. And then we used our formula. We used the fact that these two forces have to be equal, and we used that to calculate our current. Hopefully that made a little bit of sense. Here's another slightly more detailed answer on my slides. But let's keep on moving along. So one fun little thing is this force that occurs between two parallel wires was actually originally used to define the ampere, which is a lot of fun. So the ampere is that this is like the formal funky definition. So that's why it's kind of whack. But getting on our best like ha 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 voice, we can say the ampere is that constant current which, if maintained in two straight parallel wires of infinite length placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the negative 7 newtons per meter. That's all to say, basically, it's the current that if you have two wires a meter apart, it would give you a force of 2 times 10 to the negative 7 newtons per meter. Because like in the formula, right, if you do mu naught on 2 pi times 1 divided by 1, it just gives you mu naught on 2 pi, which you may remember is 2 times 10 to the negative 7. Funnily enough, we actually got rid of that. It's not defined like that, which is funny because it basically, they changed it pretty much as soon as the syllabus changed. So we're only 3 or 4 or 5 years into the syllabus and it's already wrong, which is hilarious. But it's hilarious for us to laugh at Nessa for having wrong stuff in the syllabus. However, it also shows you like science does actually change. Science is a dynamic field. There is stuff happening, and at the moment is an exciting time for physics. There's a lot of fun stuff that's actually happening in physics. it's a cool field to be involved in. So you guys have picked the right choice with your topic. So yeah, the ampere is now defined by taking the fixed value of the elementary charge, where 1 coulomb is 1 ampere per second, which is